Welcome to Lecture 3 on soft theorems. I'm splitting Lecture 3 into 3 parts. In this, the first part, I'm going to introduce soft theorems. In the second part, I'll derive a master formula from which, in part 3 of the lecture, we'll derive universal soft theorems as well as some fundamental results in quantum field theory. So this lecture is about divergent soft theorems. In lecture 1, we talked about vanishing soft theorems and Goldstone bosons. But now we'll talk about amplitudes or models in which the amplitude diverges when a momentum of a massless particle is taken to zero. And so this is the case where the soft weight, sigma, is negative. Now let's go back and think about in QFT class, where you may have learned about photon infrared divergences, for example in the context of QED. So there we learned that when a soft photon attaches to a fermion line or an electron line through these cubic interactions, then as the photon's momentum gets soft, there's a divergence. This is one of the infrared divergences that occur in QED amplitudes. The divergence takes a very particular form. It is proportional to the charge of the particle, so for an electron that would be the fundamental charge. And then there's a numerator factor here, which is the photon polarization, dotted into the momentum of the electron. And then this is divided with basically what is the propagator that sits in this diagram, namely that what comes out to be Ps dot K, so P soft dot K. And then from this expression, it's clear that when P soft goes to zero, the contribution from this diagram diverges. And you see that the reason it diverges is because the internal propagator in this diagram ends up going on shell. Now, for gluons, there is a similar behavior. For gluons, there's a soft behavior also that is divergent, and we can see this from the Park-Taylor formula that I introduced in the previous lecture. So this is again now an n.1 particle amplitude, which is color ordered, and I'll take the n plus first particle to be called S, and I'll choose it to have positive helicity. And I've written out here the Park-Taylor formula, and in this particular situation here, I picked the two negative helicity lines to be particles 1 and 2. And so that's why 1 and 2 have a special role in this formula, while all other particles are on an equivalent footing. Now we're going to take particle S momentum to be soft, so we scale it with epsilon. And in spin-helicity formalism, that means that we write epsilon times angle spinor S times square spinor S. But now we know that there's an ambiguity here. How am I supposed to take the soft limit in a spin-helicity formula? After all, in this formula, S appears in two places, but it does not appear in a way that obviously tells me which way to take the soft limit. There are some various choices one could make. For example, I could go with choice 1, where I scale the square brackets with epsilon, but leave the angle brackets alone. Or option 2, where I scale the angle spinors and leave the square spinors alone. Or some hybrid version, such as scaling both angles and square spinors with epsilon to the 1/2. Now, all of these options, this comes down to a little group ambiguity in I can scale the angle and square spinors oppositely. So physically, in some sense, they're the same. But some of them are better at detecting soft limits than others. Consider, for example, option 1. If, in the Park-Taylor formula, I scale particle S with the choices of just the square spinors, then the whole amplitude is order epsilon to the 0, and so in this option, I do not even detect a divergence in terms of what happens when epsilon goes to 0. So that's not a good choice. In some sense, the epsilon divergence that is there is cancelled by a little group scaling. In option 2, on the other hand, I detect the II divergence and is enhanced by the little group scaling. So instead of being 1 over epsilon, as you might think from a formula of this sort here, it is actually 1 over epsilon squared. But that means that the II divergence is detected. If I went with option 3, this hybrid option with the square root of both the angles and the square spinners, I also detect the IR divergence by an epsilon 1 over epsilon. But why would I make things more complicated than I have to by scaling both angles and square spinners? Maybe it doesn't matter for the MHV formula, but it certainly will matter if I look at other gluon scattering amplitudes. And by the way, who likes square roots anyway, and who would introduce them when you can avoid them? So, for this reason, we'll go with option 2. And the statement here is that for a positive helicity amplitude, so for a positive helicity soft particle, you scale by option 2 up here. And that means you scale the angles and not the squares, whereas you do the opposite for a negative helicity particle. What you get out of this is that you get a little group enhancement of the divergence rather than a cancellation than you would if you have switched for the options for the positive and negative helicity states. And if you wish, of course, to make things complicated, you could go with option 3, but anyway, just kidding. All right, so we are now going to assume that we have a positive helicity gluon that's going soft. That's what I had up in the Park-Taylor formula with my soft particle here. I'm going to scale it using option 2, where I scale the angle spinner, but not the square spinner. I'll just denote them with a hat for the soft scaling. We see that because S, particle S, angle spinner, appears twice in the denominator, I get a 1 over epsilon squared factor, as I stated before. And now I can do a very simple little rewrite where I choose to multiply and divide by the same factor of angle bracket N1. And what that buys me is that then this whole remainder factor that is left is nothing but an n particle amplitude that I would get by simply removing particle S from the n plus 1 particle amplitude that I begun with. So I have the 1 over epsilon squared. I have my n particle amplitude with S removed, and then what is left is a certain soft factor that sits out in front that contains the soft momentum as well as the states n and 1. Those are exactly the states that were adjacent to particle S. And therefore, in the color ordering, where I'm not allowed to cross any lines, those are exactly the states where S can attach. In fact, it's a nice little exercise to use the expression that I stated for QED, which is also valid for QCD in Feynman language, to then derive the same soft factor as we have for Yang-Mills. By the way, I've sort of casual here with the factors of 2, but you could of course also just put those in. All right, more generally, there are a set of universal soft theorems that I'll now describe to you. So for photons, and I'll describe photons first and then gravitons afterwards. If I have an n plus 1 particle amplitudes of photons interacting with various charged particles, then I get a leading soft factor with a soft coefficient that is called S, that I'll denote as 0, divided by 1 over epsilon squared. That's exactly the epsilon squared that we saw with the little group enhancement that I just mentioned. Then there's another universal subleading term, which has a 1 over epsilon. And in case you allow cubic higher derivative terms, a certain form, then there can be a further subleading soft theorem. Now let me just here explicitly give you what the form of S0 is. And it takes, in spin-helicity language, the form that I'm writing here. It's a sum over all charged particles with charge qk times this ratio of angle brackets, which looks very similar to what I gave you for the Park-Taylor formula, but it's not the same. In fact, this factor here is just the same as what I had before when I mentioned the QED soft factor. Now I'm using the spin-helicity formula to write down the polarization vectors, and X now is what I'll denote the reference spinner that in the previous lecture was called Q. But I can call it whatever I want. And then you see that this other bracket here, this is exactly just, these two other brackets are just from the propagator. And now when I combine and I multiply out what this angle spinner is, it will produce a square spinner, so a square bracket Ks that cancels this Ks, and I'm left with the ratio of angle spinners that you saw exactly up here. Now various factors of 2 and square root 2 that were denoted before are ignored, so that's why I have some twiddles here instead. Often those factors can be combined and absorbed into what we denote as the coupling. So these are the soft photon theorems. For gravitons, there's a similar story. There's a leading soft factor, which now has a little group enhancement that from spin 2 particles. That means that it goes as 1 over epsilon cubed. There's a subleading term that goes as 1 over epsilon squared, and there's a sub-subleading term which goes as 1 over epsilon. These all multiplies the amplitude that you had before with state n removed. So with the n plus 1 removed, with the soft state removed, but otherwise the same states. And then in EFTs with certain cubic interactions involving the gravitons, you can also have a further soft subleading soft factor, which I denote as tilde. What is the meaning here of the tilde there and there in these EFT contributions is that whereas in the standard soft theorems there's no change in the external states on the remainder amplitudes here, there will be in M tilde where the soft line attached, you can actually end up changing that particle label. But that's a more detailed story that I won't go into here. I want to make a comment about the leading soft factor for graviton, the thing that I call curly S with an index 0. It's proportional to the gravitational coupling. And then it has a factor which looks exactly as the soft photon factor but squared, which might remind you a little of what we had before. And whereas in terms of the double copy in the previous lecture. But one other thing you notice is that where the photon attaches to particles that carry charge, QK, the graviton should attach with anything with energy. And so while it does have the gravitational coupling here, it also has a factor which is basically the interaction energy of the soft particle with the K particle, namely from Mandelstam, which is SSK. So it sort of has that sense of being the same as a spin 1 soft factor squared with a coupling that involves an energy. Now, you can look up references that I'll give you separately for expressions for the sub and sub-subleading factors as well as the EFT factors. Now, going on, in the next part of this lecture, we're going to derive a master formula for the four-dimensional soft limits that will allow us to derive not only the leading soft factors for photons and gravitons. They can also, you'll have to do this in your own as an exercise, derive the subleading and sub-subleading soft factors, as well as the EFT contributions. But we'll also see that we can use these formulas, this master formula, to derive some very fundamental results about quantum field theories. So, onward to part 2.